Once again, we must calculate from first principles, in other words using this formula, the gradient of f, which is now a parabola, specifically at x equals 1. Let's have a look at this graph, the graph of our function f. What must we determine? We must find here, where x equals 1, the gradient of the function. At this point, the gradient of the red line, which is a tangent to the graph, will be exactly the same as the gradient of the graph at this point x equals 1. We want to find the gradient of the graph at the point where x equals 1. So, in our formula we will substitute 1 for x's value. In our numerator we get f of 1 plus h minus f of 1. So let's simplify these, f of 1 plus h and f of 1 first, everywhere in this formula. When calculating f of 1 plus h, we must be very careful, because remember, in our original formula, it says f of x is minus 3x squared plus 2x. So what does f of 1 plus h mean? Everywhere where we have an x, we must replace this with 1 plus h. So I get minus 3, and then in x's place I must write 1 plus h, and then square it, plus 2 times x, and instead of that x we write 1 plus h. So this gives us 2 and in brackets 1 plus h. If we simplify this, remember that that bracket is squared and it must be multiplied out, and remember the middle term. So this gives us minus 3 minus 6h minus 3h squared plus 2 plus 2h. And this gives us minus 1 minus 4h minus 3h squared. We must also calculate f of 1. Remember to substitute wherever there's an x only a 1, and this gives us a minus 1 as an answer. Now we go back to our limit formula. Instead of f of 1 plus h, we put minus 1 minus 4h minus 3h squared, and subtract f of 1, which we've calculated as minus 1. And all of this over h, and this simplifies to the limit where h approaches 0 of minus 4h minus 3h squared over h. If at this point I simplify this limit by replacing h with the value of 0, then above the line I get 0 minus 0 over 0, and this is a limit in the form 0 over 0. When this happens, I must remember to try and rewrite the expression. The way to rewrite this expression is to factorize. Here I have taken out a common h, and I can cancel out the h in front of the bracket and the h below, and this gives me the limit where h approaches 0 of minus 4 minus 3h, and if I now make h 0, then I get merely minus 4. So what have we calculated? The gradient of the function f, where x is 1, is minus 4. What does this mean on the graph of the function f? There, where x is equal to 1 of this parabola f, it has a gradient of 4. Also, this tangent will have a gradient of 4. So we know that a line that runs in this direction will have a negative gradient, and this is confirmed by the minus 4. Determine from first principles. In other words, we must use this first principles formula, the gradient of f, which is x cubed plus x, a third order equation where x equals 2. Looking at this graph, this is the graph of a third order function, we are asked to determine the gradient of this function exactly at x equals 2. So in other words, at this point. The gradient of the graph at this point will be the same as the gradient of a tangent to the graph at this point. So, to calculate the gradient from first principles of the function f, we need to make x equal to 2 in this formula. After we've substituted the value of 2 into our first principles formula, we must determine the value of f of 2 plus h, as well as the value of f of 2. F of 2 plus h is then equal to 2 plus h cubed, remember it was x cubed, and x is replaced with 2 plus h. In order to simplify this bracket cubed, I've rewritten this as a bracket squared multiplied with a bracket. It is much easier to simplify a bracket squared and then multiply that product with merely the bracket than to do it all at once. So in our next step we get 8 plus 12h plus 6h squared plus h cubed plus the bracket 2 plus h. Now we must calculate the value of f of 2, and we do this by substituting 2 into the function. So f of 2 gives us a value of 10, and now we have the answer for f of 2 and for f of 2 plus h, and we can put this back into our formula. In this step we see that the plus 10 and the minus 10 cancel out, and this gives us the limit where h tends to 0 of 13h plus 6h squared plus h cubed over h. At this point, if we substitute h as 0 into the numerator and the denominator, I get a 0 over a 0. In other words, this limit is of the format 0 over 0. Remember, when you get a limit in the format 0 over 0, we must simplify by factorizing. We can factorize the numerator by taking out a common h. Once we've done this, we can see that we can cancel the h in the numerator and the denominator. And now, if we make h 0, we get 13 plus 0 plus 0, which gives us merely 13 as an answer. So what we've calculated here is that the gradient of the function f, there where x equals 2, is 13. This means on the graph that here where x is 2, the gradient of the third order function f at that point will be 13, or the gradient of a tangent to that point will also be 13. Looking carefully at what we've done here, we've calculated the gradient of this function where x is 2, but we have only calculated the gradient of this function where x is 2. If we want to calculate the gradient where x is 1 or minus 1, then we have to go through this process again. So, next, we want to calculate a general gradient function for any value of x. So we want to see what is the gradient function of x at any general x. The question can be stated, determine from first principles, and remember, first principles implies that we must use this formula, the gradient function of f, and here f has been given. It's exactly the same one as we've just worked with in the previous example. But now, we are not given a point at which to calculate the gradient. We must calculate the gradient at any point x. To do this, we will use the same first principles formula. The value of f of x plus h we must determine for this function f and also f of x, which is exactly x cubed plus x. So let's calculate f of x plus h separately first. F of x plus h, remember, we must substitute into the original function an x plus h everywhere where there is an x. So the first term becomes x plus h cubed plus x, and that x becomes x plus h. Subtract f of x, and f of x is what has been given. So let's substitute these into our formula. In the first step, in the first blue square brackets, I've rewritten the value of f of x plus h, which is this bracket plus the next one. And if we go to the formula, then we must subtract f of x, which is the next square bracket, x cubed plus x. So in our next step, we are going to remove all the brackets and simplify. What happened here is that x cubed minus x cubed cancelled out, and there we have a positive x, and here we have a negative x, so those two cancelled out. So in other words, we got this as a final answer. As a control mechanism in this formula, we can always check to see if the last bracket has cancelled out. It should always cancel out with something from the first bracket. If it didn't happen, you must check. You might have made a sign error somewhere. In our next step, if I make h0 now, then I get 0 plus 0 plus 0 plus 0 over 0, which will give us this limit in the format 0 over 0. What does this remind you of? Then we must simplify the numerator by factorizing. How can we factorize? I can take out a common h from the numerator, and I get h outside, which can now cancel out with the h in the denominator. And if I now make h0, in other words, I determine the limit. So in the next step, I'm not going to write down the limit. Our answer is now 3x squared plus 3 times x times 0 plus 0 plus 1. Let's look again at what we've just calculated. We've calculated that the gradient of function x at any point x is equal to 3x squared plus 1. So what's the meaning of this line? This means that we can substitute any value for x, and we will be able to get the gradient of that graph f at that point. In the previous example, we calculated the gradient at 2. So if we did everything correctly, I can substitute 2 into this function and get exactly the same answer. So if x is 2, the gradient of f is therefore equal to 13. And that is exactly what we got in the previous example. So this means when x is 2, that point there, then the gradient of this graph at that point is 13. Or if I were to draw a tangent to this point, its gradient will also be 13. Now that we have a general gradient function, means I can calculate the gradient anywhere. Let's also calculate the gradient here where x is 1. Here we see that the gradient is 4. At that point, we found that the gradient was 13. So here, the gradient is steeper where it is 4. This means the graph is rising faster here.